Hello and welcome to Lecture 12 of Foundations of Artificial Intelligence. Today we're going to be primarily focused on rule-based expert systems, but we'll also get some exposure to some other expert systems. In our last lecture, we covered rules as another kind of knowledge representation, and we also introduced expert systems at a high level, talking about the what, why, and when, and then we gave a brief introduction to rule-based expert systems. In today's lecture, we're going to go through the major components of an expert system, including the knowledge base, inference engine, and some other components of a typical expert system. Then we'll take a brief tour of some other kinds of expert systems. We'll discuss the advantages and disadvantages of expert systems, and then we'll end with a brief discussion of expert system shells. So first, let's dive into some of the major components of a rule-based expert system, starting with the knowledge base. Recall from our last lecture a discussion of the basics of rules. Again, here they will commonly take the form of an if-then expression, otherwise known as an implication. And recall this high-level schematic of the parts of an expert system that we looked at briefly in our last lecture as well. We're going to start by taking a closer look here at the knowledge base and all the elements that it can include. Then we'll move on to the inference engine, and then we'll go back and provide some additional details on some of the other components such as the knowledge base editor, explanation system, and the user interface. We'll start our discussion of the knowledge base by first identifying the difference between a problem and a knowledge domain. Typically, an expert's knowledge is specific to one problem domain, for example, medicine, finance, science, or engineering. The expert's knowledge about solving specific problems is called the knowledge domain. So just to clarify, the problem domain is always a superset of the knowledge domain. The knowledge base itself holds the expertise that the system can deploy. The knowledge base can be referred to as production memory when it comes to production systems. A knowledge base is uniquely developed for a specific expert task, and this knowledge base exists independently from the rest of the expert system shell, or the other components. You can think of the knowledge base as including both the long and short-term memory of the expert system, where the long-term memory generally includes facts and data and rules that don't change throughout the course of running the expert system. The short-term memory can be thought of as the working memory. This would come into play when trying to ask a specific question of the expert system. These would include case-specific facts that are added to the knowledge base either by a user or by the inference engine in response to a query being made. Now let's go through and summarize the major parts of the knowledge base as they exist in a lot of expert systems. Here we have the knowledge base illustrated on the right, where all the items representing long-term memory are given in blue, such as rules, general facts, and questions to ask. And then our short-term memory is here in pink, which includes the case-specific facts. The rule-based part of the knowledge base includes implication rules that capture domain knowledge. The fact base of the knowledge base includes general facts that do not change. The fact base can reference a database of key information or variable values. Then there's the question-based part of the knowledge base. These are questions written in natural language. These questions can request case-specific facts from the user, and then the inference engine utilizes the question answers to determine if a given rule is going to activate. Then there's the case-specific facts part of the knowledge base. These are facts provided by a user for a given query. They can either be given as question responses when fewer facts are needed, or all of these facts can be loaded in bulk when there are many unique facts needed or available to solve a specific problem. Diving into the rule base a little bit more, it's typically a largely unordered set of non-repeating rules. Depending on the task complexity, rule bases for real-world problems may contain a few hundred to thousands of rules. Considering that we're using just if and then rules, how do we handle or situations? For example, if we want to say if A or B or C, then D. Well, in the context of a standard rule-based expert system, we would just break this expression into individual rules. In other words, if A then D, if B then D, and if C then D. Here's an example of what a rule might look like in an expert system rule base. It looks a lot like what we've seen in first order or predicate logic. In this case, if son is son of father, then father is father of son. This simple rule just demonstrates that the father-son relationship can be interpreted either way. This seems trivial, but this can be the kind of thing that you'd need to implement within your rule base in order to handle different kinds of situations. Next, let's look more closely at the fact base. This tends to be an unordered set of facts that give values for propositions or predicate statements. Facts should follow the syntax of rules so that the inference engine can match facts to be applied to the appropriate rules. Going back to our example rule, here are some facts that we might have in our fact base. Notice that son of, with two entries, corresponds to the syntax of the if part of this rule. So this fact says that Steve is the son of Joe, and Bill is the son of Dave. Now let's look more closely at the question base. This is an unordered set of questions applied by the expert system when needed to give the system a more human feel for user interaction. Typically, questions return the following user-entered values, such as yes or no, true or false, multiple choice, where the user has to pick one or all that apply, or enter a value, and that value could be an integer, float, or a text. Here's an example of what a question might look like in an expert system. Who father, answer. This is the text itself that the user will see, who is your father, and then we've delineated possible answers to that question, and the user can choose the most appropriate. This illustrates one way we could get a case-specific fact into the knowledge base to help answer a query. Next, let's move to the inference engine. The inference engine obviously plays a central role in how an expert system works. Notice that the inference engine interacts with the knowledge base, as well as the user interface. The inference engine is also known as a rule interpreter, and it's basically the thinking part or the brain of the system. It controls how the if-then rules are applied to the facts. It allows for the acquisition of further information from the user by prompting the user for further input via a natural language interface, perhaps by questions. And it can be used to come up with some hypothesis or solution, to refine a hypothesis or solution, or resolve conflict between some currently competing hypotheses or solutions. Ultimately, the inference engine is responsible for linking rules with facts to generate new facts, where new facts represent conclusions about the state of the domain given the observations. Given that we're focusing on rule-based expert systems, the inference engine is almost always going to apply forward or backwards chaining as the inference strategy. Recall from our last lecture when we discussed briefly about rule inference, there are generally two principal tasks that imply two specific control regimes. One is a forward chaining approach that's data-driven, and one is a backwards chaining approach, which is goal-oriented. Here's a table that summarizes some of the major differences between forward and backwards chaining for you to use as a reference. Understanding the difference between forward and backwards chaining, as well as understanding how these inference strategies work, is definitely a key element of this course. Recall briefly that forward chaining starts with facts in the knowledge base. Inference rules are applied by matching the facts to the if part of rules in the knowledge base, and this results in new facts being added to the knowledge base. Differently, with backwards chaining, we start with a user-entered goal to be proved. Inference rules are then applied by matching the goal to the then part of the rules in the knowledge base. This results in sub-goals that still need to be proved. We continue to work backwards to the facts until we can hopefully prove the query. We're now going to take a closer look at the components of the inference engine itself. Typically, the inference engine follows what we'd call a match, resolve, act cycle, although it's also referred to as a recognize act cycle. This cycle describes the execution of rules by an inference engine. Here's an illustration of that cycle. It includes pattern matching, followed by conflict resolution, and finally, consequent activation. The steps of what to do next are stored on an agenda. And depending on the type of inference we're doing, the inference engine might output new case-specific facts that get added to the knowledge base. Recall from our last lecture that we briefly discussed this idea of pattern or rule matching. This corresponds to this component of the inference engine. Again, matching determines the applicable knowledge in the given situation. This is the search part of the system. Rules become activated or triggered based on the type of inference or chaining being used. In this case, either forward chaining or backwards chaining. Any matched rules are added to the agenda, as we just mentioned. And again, this is a prioritized list of rules created by the inference engine. An important part of this matching process is the concept of variable binding. This is similar to binding from logic. And here, variables and rules acquire values during the matching process. So both antecedents and consequence may contain variables. For now, we're going to assume that variables are going to look like this, since this is how the Pike expert system programming language that we're going to use formats variables. Basically a $sign and a variable name. Let's go back to our example rule from before. If son of variable son, variable father, then father of variable father, variable son. And let's say that these facts exist in our knowledge base. Now for this example, let's assume that we're doing forward chaining. So we're going to look for any facts that match any of the ifs in our rule base. And in this case, we have son of Steve Joe matches if son of variable son, variable father. In order to make this fact properly match this part of the rule, we need to bind some variables. Thus the value Steve gets bound to son, and Joe gets bound to father. Now, when the consequent of this rule is activated, this part of the rule will also accept these bound variable values, meaning that we can add a new fact to our knowledge base, which would be father of Joe Steve, or Joe is Steve's father. And because this is a new temporary fact, it gets added to our case-specific facts, otherwise known as our working memory. Once a variable is bound, that variable is replaced by its binding wherever it appears in the same or subsequently processed patterns. Whenever the variables in a pattern are replaced by their bindings, the pattern is said to be instantiated, just like from logic. In forward chaining, these bindings typically persist as new facts added to that working memory. However, in backwards chaining, these bindings can be temporary as we're going about testing different hypotheses and trying to prove through backwards chaining a chain of truth values. The next part of the inference engine is conflict resolution. During the last step of matching, this process can often yield more than one applicable or matching rule that's put in the agenda. So then the question is, which one do we look at first? Or do we only want to look at one of the matching rules? For example, maybe we only want one medication to be prescribed, even though multiple medications would be appropriate. Assuming that we only want one action to fire, these matching rule instances are said to be in conflict. So now we have to use some kind of conflict resolution to pick just one for firing. In this case, we'll assume we're doing forward chaining still. One way to achieve this is to select the rule with the highest priority from the agenda. But there are different ways to assign priority, and there are different strategies that can be used to resolve such conflicts. Here's some of these conflict resolution strategies. The first is order, or the source file ordering. Basically, this just means to pick the first rule that matches in the rule base based on how the rules are actually ordered in the file. However, this tends to not be ideal or really quite a pain for very large rule sets because now you have to worry about how all the rules are ordered in the file. Then there's specificity. Here we would pick the most specific rule. By more specific, we mean that if the conditions of one rule are a subset of that of a second rule, choose the second rule. For example, if we have the rule if A and B then C versus if A then C, we'd pick the first because it's more specific. Another conflict resolution strategy is to go based on lexical order, or alphabetical or dictionary order. For many problems, this is somewhat arbitrary, but it could be useful in some domains. Another way to go about conflict resolution is to assign importance to rules. This is also known as salience. Here we want to pick the rule with the highest priority, and so rules have to be defined with some kind of priority score. This is often discouraged as it can be very hard to set up precisely in large rule bases. But if you want to, you can control the importance also by something called meta rules that serve as rules that basically tie-break conflicts. Here's an example of using importance for conflict resolution, where we have these two rules. If patient has pain, then prescribe painkillers, and this rule has a priority of 10, versus if patient has chest pain, then treat for heart disease, priority 100. If both of these rules' conditions are satisfied, then the second rule would actually be fired since it has a higher priority. Yet another conflict resolution strategy is that of recency. In this case, we want to pick the rule that was most recently added or modified, or that has antecedents most recently added or modified. The downside here, of course, is that you're going to have to require time tags in your implementation. And the last conflict resolution strategy we'll mention is refactoriness. This approach just doesn't allow the same binding instance of a rule to fire again. All right, the last part of our inference engine that we're going to look at is the consequent activation. So now once a rule on the agenda is selected, consequent activation is basically where we activate, fire, or trigger the rule. If we're doing forward chaining, we're executing the consequence of an applicable rule, and this results in a new fact being added to our case-specific facts. Once this is done, we can remove the rule from the agenda, since we don't have to deal with it any further, and the entire cycle of the inference engine ends when no more rules are in the agenda, or when there's some explicit stop command that's given to the system. Now let's revisit how forwards and backwards chaining works in the context of these rule-based systems. This should all look very familiar from our discussion of chaining from logic. When it comes to forward chaining, we're going to repeat the following. Apply all the rules to the current facts, and each rule firing may add new facts. Do this until no new facts are added. So in this very rough example, we have a fact here at the top, and we have a set of rules in our knowledge base. Fact 1 satisfies our first rule, which creates a new fact that's added to our knowledge base. This new fact then allows our next rule to be triggered, adding fact 3. Fact 3 allows fact 4 to be triggered. Fact 4 allows fact 5 to be triggered. And perhaps fact 5 is our goal, or some kind of decision or action that's going to now take place. Let's now walk through a slightly more complex example of forward chaining inference. Let's say that we start with this fact base, where A, B, C, D, and E are all facts. These facts could be hard-coded into the system, or they could have been provided by the user at the start of the query. So now we take a look at our first fact and see if it activates any of the rules. In this case it does. A activates or triggers X, so X gets added to our temporary fact base. We then see if B can trigger any rules, but as you can see here it doesn't trigger anything on its own. We then look at C, and in this case C does trigger L. So at this point L gets added to our fact base. This ends the first cycle of our forward chaining approach. You can think of a cycle as trying to add as many things as possible based on our starting set of facts. So at the end of this cycle we have all of our original facts, but now we also have X and L as facts. So now let's move on to the next cycle. Now we check our knowledge base to see if any new rules can be triggered. In this case, now we know X, B, and E, thanks to X having been added in the last round. So at this point Y gets triggered and added to our fact base. However, Y was just added, so we can't yet trigger this rule, and we don't know L and M, so that ends this next cycle. In our third cycle, we now have A, B, C, D, E, X, L, and Y, and at this point we can now trigger the Y and D rule, which lets us put Z into our fact base. At this point, Z might be returned to the user as either as the goal we were trying to prove, or maybe we were looking for some kind of recommendation, and so Z is what's provided back to the user. Notice that we didn't use all rules in our knowledge base. In this case, we never had the fact M, so this rule could not be triggered. We can illustrate this process of forward chaining via what we'd call an inference chain. So in this example, we assume A, B, and E are facts, and we have the following rules. Here A, B, and E is facts in the chain, and we can see how one fact leads to the addition of a new fact. So for example, rule 3 says, if A is true, then X is true. So now we have A, X, B, and E. To show that Y is true, we need to show that you have X, B, and E, which is why they make up this level. These allow us to add Y. All we need at this point to get to Z is to show that D is also true. Maybe we've designed our expert system to go ahead and ask the user at this point if D is true or not to see whether we can conclude Z. Or perhaps it's not true and we can't conclude Z. Now let's walk through similar examples for backwards chaining. Here are the series of steps used in rule-based backwards chaining. It'll repeat the following steps. First, see if the consequent is in the fact base. In this example, goal 5 is the consequent we're looking for, so we check to see if it's already in the fact base or not. If it's not, then we're going to find rules that have that target consequent. So in this case, this rule includes goal 5 in its consequent, and so that's what we're trying to prove. Any of these rules that have a matching consequent stack. In other words, its antecedents, or this part of the rule, becomes the new target consequent. In other words, this becomes the subgoal. So now we have to find a rule with this subgoal, which we find here. Goal 4 is part of its consequent. Or we could also see if goal 4 was already in the fact base. We basically repeat this process until a connected set of subgoals are satisfied by facts that are in the knowledge base or the fact base. So in this case, you can see the backwards chaining proceeding backwards until we find this rule where goal 1 happens to be in our fact base. Since this is in our fact base, the truthfulness propagates all the way back to our original question. Of course, it can also happen that there is no connected set of subgoals that can be satisfied by the facts. So here we'll go through a slightly more complicated walkthrough using backwards chaining. In this case, the goal we're trying to prove is Z. Here's our knowledge base with rules and our fact base. Again, these facts could be either provided up front by the user or they could be hard-coded facts in the knowledge base. Starting from Z, we find a rule in our knowledge base that has Z as its consequence. If Y and D, then Z. So at this point, we know that to prove Z, we need to also prove Y, and then we need to prove D. We'll start with Y. So now our goal is to check if Y is already in our fact base, which it's not. And since it's not, we're now going to look for a rule with Y as its consequence. So now this rule is something we need to prove also. Let's continue down this path to see if we can prove Y. To prove Y, we need to prove X, B, and E. Well, notably, B and E are already in our fact base, so the only thing left to prove here is X. So now we find a rule that has X in its consequence. Now, since A is a fact, we can now actually add X to our fact base. So now our fact base includes all of these. At this point, all the conditions of this rule to prove Y are true, since they're all in our fact base. So now we can add Y to our fact base. So now going back to the first rule we cared about, if Y and D, then Z, we now know that Y is true and D is true, so we've proven our goal of Z. And in this case, we have a successful example of backwards chaining proving the query. When you have a query fail, you could have the interpretation of failure as negation. In other words, failure to prove the query suggests that it's not true. However, failing to prove the query could also just mean that the database was incomplete or inadequately maintained, so that's something to keep in mind. Under some circumstances, there's a possibility of infinite looping when attempting to retrieve some missing information. In these cases, it's necessary to apply termination criteria that explicitly detect this and allows the system to fail gracefully. So in other words, when you're building an expert system, there may be situations where you need to be careful not to allow an infinite loop to ever occur. Notably, there's also something called mixed chaining. Some expert systems can apply both forwards and backwards chaining simultaneously. The strategy here is for the system to chain first in one direction and then switch to the other direction, presumably so that the diagnosis is found with maximum efficiency. Also, this kind of system's behavior is often perceived as being more human. When it comes to the efficiency of an inference engine, we might ask, how do we reduce the cost of the matching process? Well, one way is through something called Markov algorithms. Here, rules with higher priorities are applied first, and this allows more efficient execution of production systems. However, this kind of approach is still not efficient enough for expert systems with large sets of rules. Another approach to reducing cost of matching is to save intermediate match information. The idea here is so that matching doesn't take place again and again and again when it doesn't need to. Here we share intermediate match information between rules. We can recompute intermediate information for changes, but this requires extra memory for intermediate match information. But in the long run, this scales better to large rule sets. Another efficiency approach is to recompute matches for rules affected by change. This has been referred to as treat. Here we check changes against rules in the conflict set. This takes up less memory than REAT here above, but it doesn't scale as well to large rule sets. In general, we can make expert systems more efficient by making extensive use of hashing, or the mapping between memory and tests or rules. Now let's move away from the inference engine and go into a little bit more depth about some of the other components that are commonly included in an expert system. Here again is our expert system schematic, and we're going to go into a little bit more depth on things like the knowledge base editor, the explanation system, and the user interface. The user interface is a means of interaction between a user seeking a solution and the expert system. The interface allows us to edit facts or rules, query the system, answer questions, and be presented with solutions and explanations. The UI is directly or indirectly connected to all parts of the expert system. The user interface itself could be simple and just provide questions or answers, Or it could be more sophisticated and be some sort of menu-driven graphical user interface, or GUI. And some systems even accommodate natural language processing. This makes the system easier to use for people who might be well acquainted with the application area, but not necessarily AI systems or computer science in general. Next, we have the knowledge base editor. As previously mentioned, this is also known as the knowledge acquisition facility, and it basically provides an automatic way for the user to enter knowledge into the system, bypassing the need for explicit coding experience. Ultimately, it facilitates the integration of new knowledge and the editing of existing knowledge in the knowledge base. Also, a quick review, the explanation system is also known as a justifier. This explains the reasoning of an expert system to the user. For example, how was a particular conclusion reached by some kind of reasoning chain? This can highlight what rules were fired and what facts were deduced along the way. They can also be used to answer why was another conclusion not reached, or why a specific fact is needed if requested by the system from the user. And it can also be used to answer why a fact was not used, or maybe why it wasn't part of an inference chain. An explanation system is obviously important for situations like where a physician has to understand the reasoning for a recommendation. The explanation system component of an expert system is a major advantage over other kinds of representations such as neural network-based systems. So despite the notable success of neural network systems in many current works, expert systems are likely to remain in use for a long time as the AI technique of choice for things like safety-critical applications such as medical diagnosis, or in situations where there might be legal concerns, where a verbal defense of a decision must be available if requested. Here's a rough example of how an explanation system might be set up using a car monitoring production system as, again, a very rough example. Here we have the action stop the car, and this decision might be made based on information about whether there's overheating and whether the brakes are responding slowly. And then furthermore, the fact there is overheating might come from a combination of knowing that the heat gauge on the car is working properly and that the temperature it's reading is over 120. A user might ask, why did we come to the decision to stop the car? It can answer the question why by going back to this fact, there is overheating. The question how asks, how did we come to this conclusion, stop the car? Again, we can go back to the previous part of the chain and identify that the how comes from the fact that there is overheating. We can follow this chain of questions all the way down to the initial facts that form the basis of the chain, allowing users to get a very rich set of explanations for how a decision might have been made. So that's been our initial focus on rule-based expert systems. Now we're going to take a quick tour of some other kinds of expert systems just so you have some familiarity of what else is out there. Here's a very complex table that I'm not going to go into great detail now that illustrates some of the other major types of expert systems that are out there. Here we have the rule-based expert systems that we just covered, but there are also fuzzy expert systems, which apply something called fuzzy logic within rules, frame-based expert system, which are basically expert systems that use the frame representation that we'd already learned about, hybrid expert systems, such as neural expert systems, which basically combine rules with neural networks, or neural fuzzy expert system, which combine fuzzy rules with neural networks. While not a focus of this course, feel free to explore this table in more detail if you want to learn a little bit more about the subtleties behind some of these different methods. In the next few slides, we'll take a quick tour of some of the key points. First, we'll start by looking at this idea of fuzzy logic in brief. Fuzzy logic refers to logic that describes fuzziness, or in other words, that describes vagueness. Here, decisions are based on a degree of membership rather than a Boolean yes, no, or absolute true, false. So in other words, these are systems that do deal with uncertainty. Here, all things are described on a sliding scale of inclusion that suggests the possibility that a given statement is true or false. So again, here instead of Boolean yes or no, we have a quantitative gray area of scale, indicating degree of membership in one group or another. Each fuzzy term value of a rule's antecedent or consequent can be represented by what's called a fuzzy set. Here our fuzzy term is A, and A can have a degree of membership X that can range from 0 to 1, where our term A is 1 if X is totally an A, and A is 0 if X is not at all in A. And more commonly, A is between 0 or 1 if X is partly in A. One way to capture this idea is thinking about membership in groups defined as being short, medium, or tall. We might say that anyone over 200 centimeters is clearly a person who's considered tall. In other words, they're totally in membership A, or we'll say A is tall here. However, as we go down in height, at some point it's less certain that we might call somebody tall or medium height. But at 170 centimeters, some might consider that person tall, while others might consider that person medium height. So this is all about trying to capture the degree of membership in one group or another based on the probability of certainty that you belong to one group or another. Now let's take a look at fuzzy rules themselves. Here's a classical example of an if-then rule using binary logic. So rule 1 says if temperature is greater than 30, then the fan speed is set to 5. And rule 2 says if the temperature is less than 10, then the fan speed is 1. A similar fuzzy rule using fuzzy logic might look like this. If temperature is hot, then fan speed is fast. While rule 2 might say if temperature is low, then fan speed is low. Notice that these rules are now defined in very qualitative terms rather than precise quantitative ones. When it comes to fuzzy inference, we have a mapping of a given input to an output using the theory of fuzzy sets. This happens in 4 steps. The first is called fuzzification. Here, given some crisp inputs, we determine the degree to which these inputs belong to each fuzzy set. So a crisp input might be the exact temperature, but a given temperature might belong to a different degree to different sets, maybe based on people's different perspectives about what's cool, warm, and hot. The next step is rule evaluation. Here we take this fuzzified inputs and apply them to the antecedents. The next stage is aggregation of the rule outputs. Here we take the membership functions of all rule consequence and combine them into a single fuzzy set. This unifies the outputs of all rules. Lastly, we have defuzzification, where we transform the final output back into a crisp number or value. Notably, when we're dealing with fuzzy versus Boolean rule systems, a Boolean system that uses AND would instead use minimum in a fuzzy system. A Boolean system that has an OR would now become a max in a fuzzy system, and not X in Boolean would become 1 minus X in a fuzzy system. I don't expect you to take away all the details of fuzzy systems. I just want to give you a brief introduction to some of their basics. So when might we want to use a fuzzy expert system? Well, perhaps when we want to express expert knowledge that uses vague and unclear words like slightly overburdened, or heavily reduced, or moderately difficult, or not so old or very tall. Ultimately, fuzzy systems are easy to develop and debug, easy to understand, and easy and cheap to maintain. However, as should be intuitive, they're not at all precise. Now let's take a quick look at frame-based expert systems. Frames provide us a structured way of representing knowledge, as we've seen, as a hierarchy of inheritance. But what might we do when we want to validate and manipulate that knowledge? The answer to that lies in the methods and daemons of a frame. A method is a procedure associated with the frame attribute that is executed whenever requested. So you can think of a method as being represented by a series of commands similar to a macro in Microsoft Excel. And in general, daemons have an if-then structure, and they're executed whenever an attribute in the daemon's if statement changes its value. Inference here in these frame-based expert systems have rules serving the role of evaluating information contained in frames, and goals are established either in a method or a daemon. Next, let's talk a little bit about hybrid expert systems. There are many creative ways to create hybrid expert systems. They can involve any combination of representations, or they can involve the integration of deduction with induction methods. However, not all combinations can be expected to work. Consider for a moment that we have an expert system that's been implemented to store and work with existing human expertise. Since it's based on human expertise, it can of course be flawed. So what if we want to update our system through ongoing experience? So this is where machine learning or inductive learning could play a role in expert systems by training a decision maker through examples rather than simply pre-programming it. As a result, machine learning methods potentially have the ability to ultimately perform better than a human expert. So one way to combine machine learning with expert systems is to hybridize expert systems with sub-symbolic systems, in other words, things like neural networks. The neural networks in this situation could be used to pre-process the data and then hand it over to rules, or they could be leveraged to learn better rules. Here's one example of a hybrid system. Specifically, this is an example of a neural expert system, or a neural network-based one. So here we have some training data, and we've trained a neural network, and we have our expert system over here. However, in this case, rules can be extracted from the weights between the nodes in a neural network. Using a neural network might allow the system to deal with noisy and incomplete data better because of its generalization capability. Because we're now straying from deductive reasoning, we can really only say that a system like this is an approximation of reasoning, because we're now drawing from both deductive and inductive reasoning methods. Another example of a hybrid system is a neuro-fuzzy expert system. So while neural networks are low-level computational structure that performs well when dealing with raw data, fuzzy logic deals with reasoning on a higher level using linguistic information acquired from domain experts. As a result, neural networks become more transparent, while fuzzy systems become capable of learning through their integration. Each layer in the neuro-fuzzy system is associated with a particular step in the fuzzy inference process. So here I've just given you a brief taste of this idea of a neuro-fuzzy expert system. If this sounds appealing to you, definitely go dig around the literature and see what else you can find on this topic. Okay, in the next part of our lecture, we're going to review the advantages and disadvantages of expert systems in general. First off, expert systems use a natural knowledge representation. In other words, you get human-readable if-then rules that make up the representation. They have a uniform structure. The system itself is basically self-documenting, and each rule is an independent piece of knowledge. You could think of this as a piecewise approach, putting together a much more sophisticated system piece by piece. Depending on the expert system you're using, they can deal with incomplete and uncertain knowledge. And of course, as mentioned, later lectures will cover this idea of uncertainty. Expert systems can be developed and updated in phases, and they allow easier knowledge transfer to remote locations. Furthermore, expert systems will provide consistent answers for repetitive decisions, processes, and tasks. They're capable of combining multiple human expert intelligences through the collaboration of their development, and they allow for the centralization of a decision-making process. Some other disadvantages of expert systems. First, they may not arrive at a conclusion or know if a conclusion is possible. However, this has been a common problem in reasoning so far throughout this course. Per their definition, expert systems also work well only within a narrow domain of knowledge. They're not really generalizable artificial intelligence systems. They're also typically unable to learn or be creative, as most knowledge-based systems don't typically self-modify or improve. The reason for this is that is a very tricky thing to pull off, and therefore it's very risky in terms of potentially making really poor decisions unexpectedly. Additionally, rule search can be time-consuming and slow, and thus sometimes unsuitable for real-time applications. Also, the relationships between rules can be considered opaque. So in other words, while individual rules can be interpretable, the logical interactions among a large rule base might be perceived as opaque. This is a result of a set of rules not having an explicit hierarchical structure. So it can be difficult to understand how individual rules serve the overall strategy. Also, expert systems are typically built on an expert's past experience, the guts and intuitions, and trial and error approach. Thus, due to the fallibility of the people who put it together, the predictions, suggestions, or conclusions that it makes can also be incorrect. Some other notable disadvantages of expert systems: they can't reason about situations that are just related or entirely new. Also, knowledge acquisition can be a bottleneck for implementation, as this can be a very time-consuming and difficult process. Also, at the end of the day, some people might have a lack of trust for using expert systems, as they don't want to leave critical decisions in the hands of machines. They're also terrible at capturing common sense knowledge, as everything must be explicitly programmed. As previously alluded, there's also a general lack of flexibility and ability to adapt to changing environments or conditions or situations. Ultimately, expert systems are not suitable for all types of domains and tasks. For instance, they're not useful or preferable when there already exists some efficient, conventional algorithm to solve that task, or if the task is about computation rather than knowledge and decision making, or in situations where knowledge cannot be captured efficiently or used effectively. In the last part of our lecture, we're going to talk a bit about shells. So here again, we're going to go back to our general expert system schematic, and here in the dotted line is a part of the expert system known as the shell. As we previously mentioned briefly, the shell is a reusable or recyclable part of an expert system. You can think of this as an expert system development, tool, framework, or environment. The nice thing is that when you have a shell in hand, the developer really only needs to generate the knowledge base to develop a functioning expert system. And this is something we're actually going to get to practice in this course. So the shell simplifies the process of creating a new expert system in a faster, cheaper, and more efficient way. The major caveat here is that you have to use a representation that the shell's inference engine can reason with. And in most situations, this representation would be rules. Notably, different shells may include different components, use different terminology, they can utilize different underlying coding languages to have programmed them, as well as different syntax for implementing rules, facts, etc. So here's a quick summary of some other information about shells. Good shells also provide facilities for communication with external resources, including database management systems, spreadsheets, and graphics packages. Other non-essential but extremely useful features include ones that we've already discussed, the knowledge base editor, the user interface, and an explanation system. Here are some examples of different shells that are available out there in the world. These include Pike, Clips, PyClips, Jess, eMycin, Babylon, Exis, Vidwan, Knowledge Pro, Kvision, Age, Cass, Leonardo, XI+, Savior, and Expert Rule. In this course, we're going to learn to use the first one, known as Pike. Pike is entirely programmed in Python 2 and 3. It uses logic programming as its basis of inference. However, it does not have a knowledge base editor, a user interface, or an explanation system. Thus, the main thing we're getting out of Pike is the inference engine that we can use with a knowledge base that we're going to create. Here's a summary of this lecture. We started by going over the major components of a rule-based expert system, including the knowledge base, which includes the subcomponents of a rule base, a fact base, a question set, and case-specific facts. Then we looked at the inference engine, learning about the match, resolve, act cycle, and looking at how both forwards and backwards chaining work in the context of rule-based systems. We also reviewed some other components, including the user interface, the knowledge base editor, and an explanation system. Then we took a tour of some other types of expert systems, including fuzzy, frame-based, neuro, and neuro-fuzzy expert systems. Then we reviewed major advantages and disadvantages, and then we ended by talking about shells, which make it easier and faster to implement new expert systems. Here's today's quote. An expert is a person who has few new ideas. A beginner is a person with many. Just a reminder that the midterm paper summaries are due, and assignment 3 is now available, which covers knowledge representation, expert systems, and Pike. Please check the syllabus for the due dates of both. As always, thank you for your attention, and I'll see you in the next lecture.